Hello everyone, I am Santosh KG, Assistant Professor, Department of Mechanical Engineering, MIT, Mysore. In today's session, I am going to solve a problem on topic shear force and bending moment diagram, which comes under module 3 of subject mechanics of materials, having subject code 18ME32. The problem statement is like this: draw the shear force and bending moment diagram for a beam loaded as shown in the figure, and also locate the point of contraflexure. I repeat the problem again: draw the shear force and bending moment diagram for a beam loaded as shown in the figure, and also locate the point of contraflexure. So, the diagram given is this. Here we are having a simply supported beam AB, which is made to rest on a supports provided at point A and support provided at point B, and this beam is subjected to an UDL of magnitude 20 kilonewton per meter in the portion AC, and also the beam is subjected to a point load of 40 kilonewton at point C, and the beam it is also subjected to a point load of 20 kilonewton at point D, and the distance between A to C it is given to be 2 meters, and the distance between C to B it is given to be 2 meters, and the distance between B and D it is given to be 1 meter. So, the first step is always to convert the given UDL, uniformly distributed load, into an equivalent point load. So, the equivalent point load for the given UDL will be equal to the magnitude of the UDL multiplied by the length through which the UDL will be acting. So, here the magnitude of the UDL given is 20 and it is acting through a distance of 2. So, if I multiply 20 with 2, I will get 40 kilonewton. Now, let us try to locate what is the position of this equivalent point load on the beam. So, in order to locate the position of this equivalent point load, we need to divide the portion AC into two equal parts. So, here the distance of AC is 2 meters. So, if I divide 2 by 2, I will get 1 meter. Therefore, this equivalent point load it will be acting at a distance of 1 meter from A and 1 meter from point C. This is how we convert the given UDL into equivalent point load. So, once you convert the UDL into an equivalent point load, the next step is to find the reactions of the supports. So, here the supports are provided at point A and point B. Therefore, the reaction developed at A, we shall denote it by RA, and the reaction which is developed at B is denoted by R suffix B. Now, let us try to find the values of RA and RB. In order to find the reactions RA and RB, we will be using the equilibrium conditions sigma m equals to 0 and sigma f equals to 0. So first I will use the condition sigma m equals to 0. We always take moments at the left extreme end of the given beam. So here in this simply supported beam, the left extreme end is A. So I will take the moment about point A and I will equate it to 0. The moment effect is to rotate, and the rotation it can be takes place in clockwise direction or it may take place in counterclockwise direction. So if the member needs to be equilibrium under the action of the moments, then we can say that whatever the counterclockwise moments that are acting on a beam, so that will be equal to the sum of the moments that are acting in the clockwise direction. So we can say that the counterclockwise moments it should be equals to the clockwise moments if the member needs to be under equilibrium. So here the force 20 kilonewton with respect to A, it is going to rotate the beam in clockwise direction, and the moment due to this force is 20 into the distance of this force from point A. So the distance of force from point A is 1 plus 1 plus 2 plus 1. So it is 5. Then we are having the force RB at point B. So this RB force is going to rotate the beam in counterclockwise direction. As a result, we get the moment due to RB in the counterclockwise side. So the moment due to RB will be equals to RB into the distance of RB from point A. The distance will be 2 plus 1 plus 1. So total distance is 4. Therefore, RB into 4, it is going to create a counterclockwise moment. Then we are having a force of 40 kilonewton at point C. So this force it is going to rotate the beam in clockwise direction. As a result, we get a clockwise moment due to the force 40 kilonewton, and the magnitude of the moment will be equals to 40 into the distance between C to A is 2. So 40 into 2. Then we are having one more force of 40 kilonewton, and it is also acting in downward direction. As a result, we get a clockwise couple, and the magnitude of this clockwise moment will be equals to 40 multiplied by this distance from A, it will be 1. So 40 into 1. So 20 into 5 is 100 plus 40 into 2, it is 80 plus 40 into 1 is 40. So RB into 4 equals 100 plus 80 plus 40. So 180 plus 40 it is 220. I need the value of RB. So RB will be equals to 220 divided by 4. So 4 5s are 20, then 4 5s are 20. So the value of RB is 55 kilonewton. Now let us try to calculate the one more value of reaction, that is RA. So in order to find the value of RA, we will be using the another equilibrium condition sigma F equals to 0, and here we can see that on a given beam we are having only the vertical forces. Therefore, I use the condition sigma F suffix V equals 0. The forces acting in vertical direction, it may be an upward force or it may be a downward force. So if the member needs to be in equilibrium, then the magnitude or the summation of the upward forces should be equal to the summation of the downward forces. So in the given beam, we are having two upward forces. So one is RA and another one is RB. So we are having two upward forces. So one upward force is RA and the second upward force is RB. Now if you see the downward forces, we are having three downward forces. One is 20 kilonewton, the next one is 40 kilonewton and the last one is 40 kilonewton. So in the downward side, the forces we are having is 20 plus 40 plus 40. The value of RA we need to find and the value of RB is 55. So this equals 40 plus 40, 80, 80 plus 20, 100. Therefore, RA equals 100 minus 55. Therefore, the RA equals 100 minus 55 is 45 kilonewton. Thereby, we got the values of the reactions RA and RB. The value of RA is 45 kilonewton and the value of RB is 55 kilonewton. So once you get the values of the reactions of the supports, then we need to write the shear force diagram by calculating the magnitude of shear forces at the given salient points. I need to find the shear forces at the given salient points. So to find the shear forces, what is the convention we are going to use? The conventions we are going to use is we always move from right side, extreme right side of the beam to the extreme left end of the beam. So we start from the right end and we move towards the left end. So this is the direction of movement, and then while moving from right side to the left side, if we encounter the upward force, they should be written with a negative sign, and if we encounter the downward forces, they should be written with a positive sign. So this is the sign conventions we will be using in order to find the shear forces. When we move from the right side to the left, the points in a sequence we are going to get are, first one is D, second one is B, next is C, and next is point A. So we need to find the values of shear force at these salient points. So the first point is D. Suppose at the given salient point, if you are having a point load, then I need to find two values of shear force at that point. One by neglecting the shear force acting at that point, and second by considering the shear force acting at that particular point. So since at D we are having one point load, we will be finding two values of shear stress at point D. Now the next point we are having is B. At B we are having the point load of magnitude 55 kilonewton. So since we are having a point load at B, we will be finding two values of shear force at point B. So the next point we are having is C. At C we are having a point load of magnitude 40 kilonewton. As a result, we find two values of shear force at point C. Now, if you come to the next point, it is A. At A, we are having a point load of magnitude 45 kilonewton. Therefore, I need to find two values of shear force at point A. So, first let us try to find the shear force at D by moving from the extreme right end of the beam towards the left end. To find the shear force at D, let us try to move from right side to left side, and first, while finding the first value of shear force at D, we should neglect the shear force acting at point D. Now, I will cover the left hand portion of the point D. Now, I will move from right end to the point D. So, when we move from right end up to point D, we do not have any forces. As a result, the shear force at D is 0 kilonewton. Now, we will consider the shear force acting at D. So, when we consider the shear force acting at D, while moving from right to left, we get only one force of magnitude 20 kilonewton. Since this force is acting in the downward direction, it should be associated with a positive sign. Now, I will come to the next point, which is B, but while finding the first value of shear force at B, we should not consider the shear force acting at B. Now, when we move from right to the point B, right side up to point B, we find only one shear force at D, which is having a magnitude of plus 20 kilonewton, because it is acting in downward direction. Then, if we consider the shear force acting at B, then while moving from right to the left side, then we will get two shear forces. So, one is downward shear force of magnitude 20, and another one is upward shear force of magnitude 55 kilonewton. So, when you add these two, we get the net value as minus 35 kilonewton. The next point we are having is C. Suppose if I neglect the shear force acting at point C, and if I move from right side up to point C, then we get only two shear forces. One is downward shear force of 20 kilonewton, and another one is upward shear force of 55 kilonewton, and the summation of these two is minus 35 kilonewton. Now, let us include the shear force acting at point C. So, when I include the shear force acting at point C, then while moving from right, we will get three shear forces. One is the downward 20 kilonewton force, the second one is upward 55 kilonewton force, and the last one is downward 40 kilonewton force. So, the downward force is denoted by positive sign, so plus 40. So, if you add this, the summation will be plus 5 kilonewton. Next, we will find the shear force at A by neglecting the shear force acting at point A, and we will move from right side to point A. So, while moving from right side, the first point we are having is D. At D, we are having a downward force of 20 kilonewton. Then at point B, we are having an upward force of 55 kilonewton. Then at point C, we are having a downward force of 40 kilonewton, and also we are having one more downward force of magnitude 40 kilonewton. So, when you add them all, you will get the summation as 45 kilonewton. Next, we shall find what is the shear force at A by considering the shear force which is acting at A also. So, when you consider the shear force acting at A while moving from right side to left side, we get the following forces. The first force we get is downward 20 kilonewton force, then upward 55 kilonewton force, then downward 40 kilonewton force, then downward 40 kilonewton force, then upward 45 kilonewton force. So, when you add all this, you will get the summation as 0 kilonewton. So, these are the shear forces acting at the given salient points. Now, using these shear forces, let us try to write the shear force diagram. So, in order to write the shear force diagram, first I should draw a reference horizontal line. Once you draw the reference horizontal line, so if you locate any value above the, after writing the reference line, now if you are having any positive shear forces, they should be written above the reference line, and if you are having a negative shear force, then it should be written below the reference line. So, this reference line will be at 0. At D, we are having two shear forces. So, the first one is having a magnitude of 0 kilonewton, and second force is having a magnitude of plus 20 kilonewton. So, at D, first shear force is having a magnitude of 0 and the second shear force is having a magnitude of 20 kilonewton. Next, if we come to point B, there we get two shear forces. One is having a magnitude of 20 kilonewton and the second shear force is having a magnitude of minus 35 kilonewton. So, at B, first we are having a shear force of magnitude plus 20 kilonewton, then we are having a shear force of magnitude minus 35 kilonewton. Next, if we come to point C, there we have two shear forces. One shear force is having a magnitude of minus 35 kilonewton and the second shear force is having a magnitude of plus 5 kilonewton. So, at point C, the first shear force is having a magnitude of minus 35 kilonewton and the second shear force is having a magnitude of plus 5 kilonewton. Then at point A, we are having two shear forces. The first shear force is having a magnitude of 45 kilonewton and the next shear force is having a magnitude of 0 kilonewton. So, here the first shear force is having a magnitude of plus 45 kilonewton and the second shear force is having a magnitude of 0 kilonewton. Now, in order to get the variation of the shear forces throughout the length of the beam, join the various points we are having on the salient points. So, first we are having 0 to 20, then here we are having a constant value of 20, then the shear force will reduce from 20 to minus 35. In the portion B to C, we are having constant value of minus 35. Then at point C, the shear force got increased from minus 35 to plus 5. Then in the portion A to C, since we are having UDL, the shear force value is rising up to value 45. Then at point A, the shear force value will become 0, and this diagram, it represents the shear force diagram for the given beam under the given loading. So, the shear force diagram, it represents the variation of the shear force throughout the length of the given beam. This shear force is having a positive value in this region and negative value in this region, and it is having a positive value in this region. After writing the shear force diagram, now let us write the bending moment diagram. So, in order to write the bending moment diagram, first I should find what is the value of the bending moments at the given salient points. So, next I am going to find the bending moments at the various salient points. So, here also we will be moving from right side to the left side, and while moving from right to left, if we encounter with a upward bending, then it should be considered with a positive sign, and if you are encountering with a negative bending or a downward bending, then it should be considered with a negative sign. While moving from the right side to the left side, the various salient points we get in a sequence are: the first point is D, then we are having point B, then we have point C, then we have point A. Again, to find the bending moment at D, we move from right side up to point D. Since there are no forces, we do not have any moments at point D. Now, we will come to point B. So, when you come to point B, while moving from right to left, we are having a 20 kilonewton force at D. So, this 20 kilonewton force multiplied by distance 1 meter, it is creating a moment which is trying to bend the beam in downward direction. So, since this moment is bending the beam in downward direction, it should be associated with a negative sign. Therefore, minus 20 into 1 is minus 20 kilonewton meter. Then we will come to the point C. So, if you come to point C, while moving from right to left, we get 2 points, one at D and another one is B. At D, we are having a force, downward force. So, it is minus 20 into its distance from C is 3. The another force is an upward force of 55 kilonewton, and it is creating a moment of magnitude 55, and its distance from C is 2. So, minus 20 into 3 is minus 60, and 55 into 2 is 110. So, if I subtract 60 from 110, I will get 50 kilonewton. In order to find the bending moment at A, we will move from point D, which is at the right end, to the point A. So, while moving from D to A, the first force we are having is a downward force of magnitude 20 and its distance from A is 5 meters. So, the moment due to 20 kilonewton force which is acting in downward direction is minus 20 into 5. Then at B we are having an upward force of magnitude 55 and its distance from A is 2 plus 1 plus 1 which is 4. Then the next point we are having is C. At C we are having a downward force of magnitude 40. So, minus 40 and its distance from A is 2 meters. So, minus 40 into 2 is the moment due to this minus 40 kilonewton force. Then the next force we are having is a downward force of 40 kilonewton and its distance from A is 1 meter. So, if you add all this, you will get the total moment that is acting, total or the net moment that is acting at point A. So, minus 20 into 5 is minus 100 plus 55 into 4 is 220 minus 40 into 2 is 80 minus 40. So, minus 100 minus 80 minus 40 is minus 220 plus 220. So, the summation is 0. Therefore, the net moment acting at point A is 0. Using these moment values, let us try to write a bending moment diagram which indicates the variation of bending moment throughout the length of the beam. So, in order to write the bending moment diagram, first I should write a reference line here. Then we should mark the bending moments acting at various salient points. So, if the bending moment is having positive value, then it should be written above the reference line, and if it is having a negative value, then it should be written to the downward side of the reference line. So, at point D we are having a bending moment of magnitude 0. Then at point B we are having a bending moment of magnitude minus 20. At point C we are having a bending moment of magnitude plus 50 kilonewton meter, and at A we are having a bending moment of magnitude 0. Now, join all the points to get the variation of bending moment throughout the length of the beam. Join 0 to 20, then 20 minus 22 plus 50. Then here, since we are having UDL load, the variation in this portion for the bending moment is a parabola. This line, it is a parabolic variation in the region of UDL. So, the bending moment is having a positive value in this region and negative value in this region. This completes the drawing of the shear force and bending moment diagram for the given simply supported beam loaded as shown in the figure. So, the next thing we need to determine is the point of contraflexure, and we need to locate it on the beam. So, we need to locate point of contraflexure. So before locating the point of contraflexure on a beam, first let us see what is the definition of the point of contraflexure. The point of contraflexure is a point on a bending moment diagram where the bending moment is 0. I will write the definition here. Point of contraflexure, it is a point on bending moment diagram where the bending moment is 0. This is the bending moment diagram we are having. So in this bending moment diagram, we can see the value of bending moment is 0 at this particular point. So from this point, I am going to write a projection line and I will locate the point on the beam. So this is the point where we are having 0 bending moment on the beam, and I will call this point as E. So in this given beam, E represents the point of contraflexure. So it is a point where the value of the bending moment is 0. Let us say the bending moment, or let us say the point E, it is at a distance of x from point D. So in order to locate the point, first we shall assume the distance in general. Let point of contraflexure E is at a distance of x from point D. From the bending moment diagram, we can see that the bending moment value at point E is 0. The value of bending moment at point E is 0. So we can try to take the moment at point E and we shall equate it to 0 in order to get the value of x, because the moment at point E is 0. Now while moving from right side to left side up to point E, we will be having two forces. So the first force is 20 kilonewton downward force at D, and the second force is 55 kilonewton upward force at B. So due to this 20 downward force of 20 kilonewton, we get a moment of magnitude minus 20 into the distance from point E is x. Then at B we are having an upward force of magnitude 55 kilonewton, and its distance from point E will be equals to x minus 1, and it is creating an upward bending. So I have written it with a positive sign and its summation is 0. Since this minus 20 into x is having a negative sign, I will send it towards right side. So 55 into x minus 1 equals 20 into x. Now you multiply 55 with the terms inside a bracket. Therefore I get 55 into x minus 55 equals 20 into x. Send the 20x towards left side and 55 towards right side. So 55x minus 20x is 35x equals 55, or the value of x is 55 divided by 35. So when you divide 55 by 35, you will get the value as 1.571 meters. Therefore, the point of contraflexure is located at a distance of 1.571 meters from point D. And this completes the problem. We have written the shear force diagram, bending moment diagram, and also we located the point of contraflexure for the given simply supported beam loaded as given in the figure.